Hi everyone, I'm Ryan. I'll be presenting Segment Anything, SAM. So in machine learning, we often talk about foundation models, models like GPT-4 that work on almost any text task. SAM is the first true foundation model for image segmentation. It allows us to isolate any object in any image, zero shot, just by clicking on it. So I'll talk about the motivation. Why do we need this? Before SAM, segmentation was fragmented. If you wanted to do segmentation over deep sea divers, you trained a diver model. If you wanted to segment cells, you trained a cell model. This approach had two flaws. One, there was poor generalization. Models failed on data they hadn't seen before. And two, there was an annotation bottleneck. Labeling masks pixel by pixel is excruciatingly slow. Meta's goal was to unify all these tasks into one promptable model. Their core innovation was redefining the task itself. Instead of just taking an input image and transforming it into an output mask, they defined something called promptable segmentation. The model takes advantage of an image and a prompt as input. That prompt can be a specific point, so a user clicks on an object or in the foreground or background to include or exclude regions, a bounding box, as well as raw text like the cat. The model must return a valid segmentation mask for that prompt, even if the prompt is ambiguous. And so now I'll talk about the image arc or the model architecture. The architecture relies on three components designed for speed. There is an image encoder, which is a visual VITH. This is the heavy lifter. It runs once per image to create an embedding. It takes about 0.15 seconds to run and complete. On the other hand, there's something called a prompt encoder. This handles the clicks and boxes. It is incredibly lightweight. So again, if you remember, the input takes a prompt and an image. And now we talk about the mask decoder. And this is where everything really happens. It's the magic. It combines the image embedding and prompt embedding using a lightweight transformer. The most crucial part of this is that because the decoder is so fast and is on the order of milliseconds, once the image is processed, you can interact with it in real time in a web browser. But a model is only as good as its data. There wasn't enough data that existed to train a foundation model, so they built a data engine. It had three components. An assisted manual stage where annotators used a basic SAM version to click objects and label them faster. A semi-automatic stage where the model automatically labeled the easy stuff, like skies, and humans focused on the hard stuff. And then there was a fully automatic stage. Finally, the model was so good it just labeled everything on its own. This loop allowed them to generate data 100 times faster than traditional methods. The result of that engine is SA1B. It contains 11 million images and 1.1 billion masks. To give you context, this is 400 times larger than the previous largest dataset, Open Images. This sheer scale is why the model generalizes so well. It has seen almost every shape and texture imaginable. And here's the proof. They tested SAM on 23 new datasets it had never seen before, and it performed exceedingly well. The graph on the left shows SAM in teal versus RITM, the previous SOTA. SAM consistently matches or beats the supervised models. It works out of the box on medical, X-rays, or satellite imagery without any fine-tuning. A unique feature is how SAM handles uncertainty. If I click on a person's shirt, do I mean the shirt or the person? Most models would guess one and might be wrong. SAM is designed to output three valid masks simultaneously. So the subpart, which is the shirt button, the part, the shirt, and or the whole, the person. It scores them and lets the user decide. This handles the inherent ambiguity of the real world. And in summary, SAM solves the generalization problem in computer vision. It is efficient, it's real-time in browser, it is promptable with flexible inputs, and it is trained on the largest mass dataset in history. It has effectively become the pre-processing layer for the entire field of computer vision. Thank you. Here are my image sources and any questions?